Question 61 asks to calculate the concentration of H3O plus in a solution that contains 5.5 times 10 to the minus 5 molar OH minus. Identify the solution as acidic, basic, or neutral. So in this case, we are going to use the fact that the concentration of H3O plus multiplied by the concentration of hydroxide at 25 degrees is equal to minus 10 to the minus 14. So we can solve for H3O plus in this example concentration by taking 10 to the minus 14, dividing that by our hydroxide concentration, 5.5 times 10 to the minus 5 molar, and that equals 1.8 times 10 to the minus 10 molar. Then it asks to identify the solution as basic, acidic, or neutral. One thing you can tell is that the amount of base that we have is way more than the amount of acid that we have, way more hydroxide than there is H3O plus. That means the solution is going to be basic. Question 22 wants us to write the conjugate acid for A and B and the conjugate base. Conjugate acid is just the same compound with an additional H plus added onto the structure. So the conjugate acid for this would be CH3CH2NH3 plus. This is a amine base. Next we have HPO4 2 minus. If you add an H plus, this becomes H2PO4 minus 1. For C and D, write the conjugate base. We have to remove H plus, so it's sort of the same process in reverse, which is CO3 2 minus, and HPO4 2 minus becomes PO4 3 minus, which is phosphate. #63. What is the pH of a 0.050 molar triethylamine solution? The Kb for triethylamine is 5.3 times 10 to the minus 4. The fact that it gives you a Kb suggests that it's going to be a weak base. And what I'm going to do is abbreviate this just to B. B is going to be my symbol for a neutral weak base. Now, this weak base, like all weak bases, will react with water to form an equilibrium that generates BH plus along with some hydroxide. How do we know it's an equilibrium? Because both things on the left are weak. Water is a weak acid or a weak base. In this case, it's acting as a weak acid. And our base we know is weak because it comes along with a Kb. Anytime you have an equilibrium situation like this, we have to use an ICE table, ICE, not ICF, and all of the numbers that are in that table have to be in units of molarity, not in terms of moles. Moles is for ICF, molarity is for ICE. So we're going to be going ICE here, and we're told that our initial concentration of base is 0.050 molar. Don't care about water. These two things will be 0 initially before this thing starts to dissociate. Some of the base will react with water to dissociate and make those ions. So we don't really know how much yet. So we'll call that X. It'll increase by the exact same amount X on the right. So that at equilibrium we have 0.050 molar minus X along with X and X. We know that our Kb, which is 5.3 times 10 to the minus 4, will be equal to x squared over 0.050 minus x. Now this is a kind of equation that would be great if we could simplify it, and we should always look when we get to this stage of an ICE problem to see if we can eliminate that minus x, because it simplifies the math actually quite a bit. It allows us to avoid using the quadratic formula. We have a test. We take the number we're subtracting x from, which is 0.050, and divide it by the k value, which is 5.3 times 10 to the minus 4. That number has to be greater than 400, and if it is, we can eliminate that minus x. If it's not, we have to multiply it through and do the quadratic formula. This works out to be 94, so unfortunately we're stuck with what we got. So what we want to do is multiply this through and put it in the form ax squared plus bx plus c, and when we do that multiplication out, we get 0 equals negative x squared minus 5.3 times 10 to the minus 4x plus 2.65 times 10 to the minus 5. So our value for A is minus 1, B is minus 5.3 times 10 to the minus 4, and C is 2.65 times 10 to the minus 5. So we stick that into the quadratic formula, which spits out a value for x of 0.00489. Keep in mind when you do the quadratic formula, it actually gives you two different values for x, but only one of them will make sense. For example, often the other root is a negative number, which doesn't make any sense because you can't have a concentration of something as a negative value. So pick the one that makes sense. X is equal to our concentration of hydroxide at equilibrium. So this question wants to know the pH. From X, we can actually get the pOH, which is the minus log of the concentration of hydroxide, which is the minus log of, therefore, X, which works out to be 2.31. Our pH is 14.00 minus pOH equals 14.00 minus 2.31 equals 11.69. So that's the pH of our solution. Does that number make sense? Well, yes, it's above 7, and we know we have a base in water, so we expect a pH that's above 7. So I think so far so good. Question 64. Butyric acid is responsible for the odor of rancid butter. A solution of 0.25 molar butyric acid has a pH of 2.71. What is the Ka? So butyric acid is a weak acid. It's asking for the Ka. It always goes along with weak acids. This doesn't give us the structure of butyric acid, but we actually don't even care at this point what the structure is. We can just abbreviate this as HA, which is our generic weak acid. So HA, like all other weak acids, will react with water to establish an equilibrium that generates H3O plus and the conjugate base A minus. We know it's equilibrium because both things on the left are weak. When we have equilibrium, we have to work on molarity, and we do an ICE table. Initially, HA concentration is 0.25 molar, and we use 0 and 0 for the values of H3O plus and A minus. Some of the HA will react, so you'll lose some amount X, and you'll increase on the right by some amount X, so that at equilibrium you have 0.25 minus X, X, and X. Our Ka will be equal to x squared over 0.25 minus x. And at this point, we don't actually know what the Ka is. We're not asked to solve for x. We're asked to solve for Ka. And it does so by giving us the pH at equilibrium, and the pH at equilibrium we can use to determine what x is, because x is the concentration of H3O plus. So x is going to be equal to 10 to the minus pH, which is 10 to the minus 2.71, which is 0.00195. So we take that value for x, we plug it into that equation to solve for Ka, 0.00195 squared, over 0.25 minus 0.00195. That gives us 1.53 times 10 to the minus 5. That will be our Ka value for this acid. Question 65 says a 0.10 molar HF solution is 8.4% ionized. HF is a weak acid. It wants the H3O plus calculation, concentration. So HF will react with water. Weak on both things are weak on the left, so we use equilibrium. H3O plus F minus, and we're starting out with 0.10 molar HF. It's telling us in the problem that this ionizes to 8.4%. So that when this is all done, the amount of H3O plus is going to be equal to our original concentration of HF times 8.4%, which is 0.084. That gives us 0.0084 molar H3O plus once this is done ionizing, establishing an equilibrium. That's all it wants, actually, is the H3O plus concentration. It's not asking us to go any further and convert that to pH, although we could definitely do that if I'd wanted to. Question 55 says, calculate the pH of a 0.021 molar NaCN solution. So here we're given a salt. We're given NaCN. NaCN, according to our solubility rules, will be a strong electrolyte. It'll dissociate completely in water to Na plus and Cn minus. So the sodium plus, being a group 1 metal, will have no impact whatsoever on the pH. The cyanide ion, however, the anion, we're told in the question that its conjugate acid has a Ka, meaning it's going to be a weak acid. That means that cyanide has got to be a weak base. So once this 0.021 molar NaCN dissociates in water, you're left with cyanide, which is a weak base, which will react with water, establish an equilibrium, and create hydroxide. Okay, so when this has dissociated, your concentration of Cn minus initially is 0.021 molar, which is the same as we have for our NaCN concentration. All right, so that cyanide is generated. It will react with water, establish an equilibrium to make HCN plus hydroxide. We have weak things on the left, so this is an equilibrium. This means this is an ICE table, ICE. And our initial concentration is 0.021 molar, 0 and 0. The initial hydroxide is actually not 0, it's 10 to the minus 7, but it's small enough that we can ignore it. C is minus X plus X plus X, add equilibrium, 0.021 minus X, X, and X. The Kb for Cn is equal to X squared over 0.021 minus X. So first problem we might recognize now is we don't know what the Kb is for this compound. However, we have the Ka for the HCN, so we can use that. We know that Kb is going to be equal to Kw over Ka of its conjugate acid, which is provided in the question. Kw is 10 to the minus 14 divided by 4.9 times 10 to the minus 10. And that gives us a value for Kb of 2.04 times 10 to the minus 5. Okay, great. So now we can rewrite this as 2.04 times 10 to the minus 5 equals X squared over 0.021 minus X. Once again, we would love if we were able to remove that little minus x. So we're going to do that test to see if that's an okay thing for us to do. So that test I'm going to do off on the side in green. So the number x is being subtracted from is 0.021, dividing by the k value, which is 2.04 times 10 to the minus 5. And that works out to be 1029. That is greater than 400. So we are happy because we can eliminate that little minus x. And this equals x squared over 0.021. That greatly simplifies the calculations. So now we can say that so x squared will be equal to 4.28 times 10 to the minus 7. X is the square root of that, which is 6.55 times 10 to the minus 4. If you remember from the previous page, X is equal to the concentration of hydroxide at equilibrium. So what we can do is find pOH by taking the negative log of X which gives us 3.18. Our pH is 14 minus the pOH, 10.82. And that's it for question 66. 67, write the equations for the net ionic reaction that occurs between the following species: NH4+, and NaOH. So each of these are being mixed together and both of these will dissociate. And so what's going on here is the Cl- and the Na+ will just be spectator ions. They don't engage at all in the reaction. And this should look like NH4+. Forget about the Cl because it's a spectator ion, and the hydroxide from the other side will react to make ammonia plus water. HCN and KOH. HCN doesn't have spectator ions, but KOH does. It'll react with hydroxide to make cyanide, as well as a molecule of water. Last, you have NaOH and an HF-NaF buffer. So what we have present here is hydrogen fluoride, sodium fluoride, and NaOH all mixed together. But the sodium hydroxide is only going to react with the HF part of the buffer. It's not going to react with the F-. So the reaction with the strong base will be with the weak acid. So the NaOH, it's going to react with HF. And we're going to write the NaOH just as OH- because the sodium will be a spectator ion. We have something strong on the left, which is the hydroxide, so we don't use an equilibrium arrow. This makes F- plus water. Question 68, which one of these salts will form a basic solution on dissolving in water? So this is examining each of these salts and looking to see if it produces an anion typically that is going to be a weak base. First one is NaCl. That'll dissociate to Na+ and Cl-. Sodium plus is a group 1 metal. It has no effect on the pH. And Cl- is the conjugate base of a strong acid, which was HCl. That means it's what we call infinitely weak. And infinitely weak bases do not have any impact on the pH, so we would expect a sodium chloride solution to be neutral. Second, we have KClO4. This will dissociate to K+ and ClO4-. ClO4 minus is the conjugate base of perchloric acid, which is a strong acid. This is also infinitely weak, therefore also that will have no effect on the pH. Potassium plus is also a group 1 metal, just like sodium, so it has no effect on the pH. So we would expect B for potassium perchlorate solution. Have I been calling it chlorate? It's perchlorate solution. We would expect that the pH of that solution would also be neutral. For C, we have LiBr, lithium bromide, reacts to make Li plus Br minus. Group 1 again for lithium, and Br is the conjugate base, again, of a strong acid. This is HBr. Therefore, Br minus is infinitely weak, no effect on pH. Also, this would make a neutral solution. D, we have NH4, NO3. This would dissociate into the ammonium cation plus the NO3 anion. The NO3 anion is the conjugate base of a strong acid, which is nitric acid. Therefore, that will have no effect on pH. It's infinitely weak, and we can ignore any impacts of NO3 minus. The ammonium cation, however, is a weak acid. And as a weak acid, what it can do is generate H plus in solution. It'll dissociate partly in water, and it'll create an acidic solution. So we expect this one to create an acidic solution. That's not what the question asks. It wants a basic solution on dissolving in water. So D is probably going to be the answer since it's the only one left. But let's look at it anyway. We have NH4ClO. That's the hypochlorite anion. That makes NH4 plus and ClO minus. NH4 plus is a weak acid, as stated above, so this should create an acidic solution, but the ClO minus is not the conjugate base of a strong acid. In fact, it's the conjugate base of a weak acid, as you can see in the question, since it has a Ka value attached. So this has a weak acid and a weak base. Which one's going to win? Is the solution going to be acidic or basic? What you need to do is compare the Ka of the acid with the Kb of the base. Whichever one is larger is going to tell you the which one's going to win. So for NH4 plus, the Ka is not given in the question, but it gives you the Kb for the conjugate base. So the Ka is Kw over Kb, 10 to the minus 14 over 1.78 times 10 to the minus 5. Which is equal to 5.62 times 10 to the minus 10. We're going to do the same for the ClO minus, the hypochlorite anion. The Kb is equal to the Kw over Ka of the conjugate acid. 10 to the minus 14 divided by the conjugate acid, which is given in the question, is 3.98 times 10 to the minus 8. Is equal to 2.51 times 10 to the minus 7. That Kb value here is much larger by around a factor of 1,000 or so compared to the NH4 plus. 3 orders of magnitude different. It's a bigger number, therefore the base part of this salt is going to win out, and you're going to have a basic solution. So that means the correct answer here is E. Question 69. Calculate the pH of a buffer solution prepared by dissolving 0.20 moles of cyanic acid, HCNO, and 0.80 moles of sodium cyanate in enough water to make 1 liter of solution, and it gives us the Ka of the acid. So this is a buffer solution because we have both significant amounts of weak acid as well as its conjugate base. That means to solve for pH, we use the Henderson-Hasselbalch equation, which is pH equals pKa plus log of the base, the weak base, over its conjugate acid. That is equal to the minus log of the Ka of the acid, which is provided, 2.0 times 10 to the minus 4, plus log of the concentration of the base. Tells us we have 0.80 moles of base in 1 liter of water. And divided by the acid, we said we have 0.20 moles in 1 liter, which is 0.20 molar. Molar units will cancel, and what we're left with is 4.30 as our pH for this buffer solution. Question 70, we have 500 milliliters of a buffer solution containing 0.20 molar acetic acid and 0.30 molar sodium acetate. What will the pH of the solution be after we add some sodium hydroxide? So we're adding strong base into this buffer situation. Strong bases will react with acids, so we have acetic acid present to begin with that will react with this sodium hydroxide. Whenever you do a titration question like this, when you're adding, I guess it's not technically a titration, but whenever you're adding a strong base or a strong acid to a weak acid or a weak base, like we're doing in this case, we start out always by drawing a neutralization reaction and doing an ICF table for that neutralization. So the acid that's present is CH3COOH. Will react with the sodium hydroxide that we're adding. This will produce CH3COO minus plus water plus Na plus. Why did I use a regular arrow here and not an equilibrium arrow? Because we have something strong on the left. NaOH is a strong base. That means it's not going to be in equilibrium. It's not going to be an ICE table. It's going to be an ICF table. And everything we put in this table has to be in units of moles, not in units of molarity. So let's find the moles of what we have. The moles of acetic acid, which I'll call HA, is going to be equal to the concentration times volume. Concentration of acetic acid is given as 0.20 molar. The volume is 500 mils, which is 0.500 liters, equals 0.10 moles. Put that in our table, 0.10 moles at the beginning. Same thing, moles of the conjugate base, A minus, which is the sodium acetate, is concentration times volume, is 0.30 molar times 0.500 liters, is 0.15 moles. Put that in our table. And we don't care about water or sodium plus because neither of them will have any impact on the pH of the solution. Sodium hydroxide will. So the moles of NaOH, it says we added 20 mils of 1 molar. 1.00 molar NaOH, and we've added 20 mils, 0.20 liters, equals 0.020 moles. That goes into our table. All right, we don't use X's here. This is not an ice table. This will react 100% to go to the right until we run out of limiting reagent. The one here that is present in lesser amount is the NaOH, so it's going to be the one to run out first. 0.020 moles. The acid will go down by the same amount. And our conjugate base will go up by that amount. So the final amount here is going to be 0.08 moles. 0 for NaOH, it's completely neutralized. And that looks like 88. No. So that should be 0.08 moles. And on the right-hand side, we have 0.17 moles. So now we have a buffer situation. We have a conjugate acid as a weak acid along with its conjugate base. So we can stick these numbers directly into the Henderson-Hasselbalch equation. We know that pH equals pKa plus log concentration of the base over the concentration of the acid. Another way we can write this actually is pKa plus log moles of base over moles of acid, because the ratio of the concentrations is going to be identical to the ratio of the moles because they're both in the same volume. So that equals the pKa, which is the minus log of Ka, which is given in the question as 1.8 times 10 to the minus 5, plus log moles of base, which at equilibrium, or I shouldn't say equilibrium, after the neutralization reaction is done, 0.17, and before the reaction's done, the acid after the reaction's done is 0.08. And if we calculate that, we get 4.74 plus 0.33 is 5.07 for our pH of the solution.